Welcome back, and today we're going to take a look at chemical reactions. And this will be a little bit of a break from mathematics right now. You just did a whole chapter on empirical molecular formulas and how you found the number of atoms and whatnot. And now we're going to start taking a look at the reactions themselves. So we need to go back and revisit what's a physical change and a chemical change. And recall that a physical change does not change the molecule, that no bonds are broken. Often it's just the state of matter changes. In other words, if you take a look at this top diagram right here, this is going to be probably water. You've got your two hydrogens and your oxygen, and notice that the molecule itself is exactly the same on both the reactants and the product side. So that would be an example of a physical change, probably going from liquid to gas. Compare that to the bottom one, where at this point right here you can see that you've got two of the little red atoms with a blue atom, as opposed to on the product side, where now all of a sudden very different substances present. And so this would be an example of a chemical reaction. There are going to be 4 signs that a chemical reaction may have occurred. The first is going to be a precipitate, and what a precipitate is it's usually a solid that if you centrifuge it, you can see that the solid forms, or it'll appear real cloudy. So that's where you've taken 2 aqueous solutions and formed a solid. A gas can form without heating, where all of a sudden, if you've ever added like Alka-Seltzer to water and it starts fuzzing, that would be an example of a chemical reaction. Energy is released or absorbed. That could be in the form of heat, or it could be in the form of light. If all of a sudden you see a sparkler, like in the 4th of July, that would be an example of a chemical reaction when energy is released in the form of light. And then finally, if a permanent color change occurs, that would be another indicator of a chemical reaction. Now let's take a look at a few examples and some videos of different types of reactions. Okay, there's a convention that we're going to be using, and that will be that the reactants, or the materials that you're starting with, will be on the left-hand side. A reaction would be indicated with an arrow going to the right, forming products. It's going to be important that we balance our chemical equation so that we have the same number of atoms on both the reactant and the product side. And then it's always important to include the physical state. And so the physical state would be a solid, liquid, gas, or an aqueous solution. And more often than not, you're going to find your substances will be present in an aqueous solution. And that just means that it's dissolved in water. Okay, now we have a chemical reaction, and it's going to be, okay, let's stop that and try it again. All right, now let's practice writing a balanced chemical reaction. In this example, we're going to have element A and element B. Element A is blue, element B is red. Looking on the left-hand side, which is the reactant side, do you notice anything about how B is when it's by itself? And you can see that there are 2 B atoms together, or 2 blue, pardon me, and then over here I've got 2 red, which means that these are both diatomic molecules. So when I was writing down the reactants, I'm going to say that this is, whoops, let me get a pen. How about this? I'm going to say this is A, and I'm going to put the little subscript 2 down here to indicate that it's diatomic, as is B. So I've got my 2 reactants on the left-hand side, and now let's see what we make for a product. So for a product, I'm going to make this A3B. Those are the molecules that I'm making. I've got 3 of the A elements combined with 1 B. Now, once we have our correct formulas, we're never going to change that. So in order to balance it, the way we're going to balance it is with the coefficients that go in front of the molecules or compounds. Okay, so let's take a look at this, and we count them up, and I've got a total of 6 molecules, each with 3 of the blue, or the A's. So there we go. So I'm using up 6 of these guys. All right, 6 of the A elements. Come over here. Now let's take a look at this. I'm going to have 2 of the B's, so that's going to be left as 1, and I'm going to need 3 over here, like so, and I've got a balanced equation. You're going to take 3 times the 2, that means I've got 6 atoms of A. 2 times the 1, I've got 2 B's on the reactant side. 2 times the 3, I've got 6 of element A, and I've got 2 times the B. Remember the distributive property there. And you can see they balance. Now I'm not worried about how many I have over here, because in this case I've just got lots and lots of extra of element A, which is okay. That just means what's my limiting reactant in this case. So now let's practice how to balance a reaction. The very first thing that you want to do is you want to write the unbalanced chemical reaction with the proper formulas first. This is going to be key. So let's take a look at this example, and what we've got here, I've got sodium reacts with chlorine to produce solid sodium chloride. All right, so I'm not told otherwise, so I'm going to assume that sodium is in the solid state because it's an element. It's a metal, pardon me. It's on the left-hand side. We're at room temperature. I'm going to say that it's solid. Plus chlorine. Chlorine is one of our 7 diatomics, so I need to remember that it is a diatomic molecule, and it is going to be in the gaseous form. And if you look on the periodic table, you'll see that it's one of our gases in the nonmetals. All right, and we're going to make sodium chloride. Sodium is in the first column. It makes a +1 ion. Chlorine is in the 7th column. It makes a -1. That means that I need 1 sodium for 1 chlorine. And it's going to be solid because you were told it made solid, sodium chloride. Okay, now, real quick, how come I didn't do this? This is a popular thing, but it's not correct. And the reason is that while chlorine is diatomic when it's all by itself, as soon as it's within another, when it's reacting with another element, it's got to follow the octet rule. It's going to behave the way it's supposed to. It's only when it's by itself is it a diatomic. So let's go ahead and erase that off of there. All right, we've done our first step. All right, now we're on to step 2, and step 2 is now we change the coefficients, never the subscripts, but the coefficients until they're balanced. All right, so real quickly, we look at this. I've got 1 sodium on the left. I have 1 sodium on the right. I have 2 chlorines on the left, and right now I have 2 chlorines on the right. The way I make it 2 is by putting it in front. Okay, that's the coefficient. But as soon as I do that, while I've balanced out the chlorines, what's no longer balanced? And that's going to be the sodium. So now we have to come over here, changing the coefficient only, and I put a 2 in front of there, in front of the sodium on the reactant side. Okay, do a quick check. I've got 2 sodiums, I've got 2 chlorines, I've got 2 sodiums, and I've got 2 chlorines. Remember, the distributive property will occur with that coefficient. All right, now let's go ahead and try some more practice. Okay, so now we have a couple more to practice with, and so now we want to balance. We've got zinc is going to react with silver nitrate. Since the silver nitrate has the AQ behind it, that means it's aqueous, which means if you were to see it, it would just look like a clear solution. It would just look like water because the silver nitrate has dissolved in it. All right, we're going to form zinc nitrate and silver. Now, the one nice thing about this is look at the nitrates as if it were one unit. In other words, don't start separating the nitrogens and the oxygens and whatnot. So you take a look over here, and do you see how we've got 2 of the nitrates? So I'm going to put a 2 in front of the silver so that I've got 2 of the nitrates. Now that knocks the silver out of balance, so now I've got to come over here and put 2 like so. And then let's put a 1 here and a 1 here because that doesn't change. Now count real quick. I've got 1 zinc on the left, I've got 1 zinc on the right. 2 silvers on the left, 2 silvers on the right. 2 nitrates on the left, and then I've got 2 nitrates on the right. All right, let's try the next one. I've got nitrogen and hydrogen. Nitrogen and hydrogen are both diatomics. However, when they combine to form ammonia, all of a sudden it's just going to require 1 nitrogen with 3 hydrogen atoms. All right, first things first, let's go ahead and make the nitrogen, okay? So I put a 2 in my coefficient in front of there like so. The only thing is that just knocked the hydrogens out of whack. How many hydrogen atoms do we have when you have 2 ammonias? And you should recognize that we've got 6 hydrogen atoms, which means I'm going to need 3 hydrogen molecules to take care of this. All right, let's do the next one. We've got sodium chloride and silver acetate, and oh, I got a typo there. The 3's not a subscript. So let's take a look at this. I've got 1 sodium on the left, I've got 1 sodium on the right, I've got 1 chlorine on the left, 1 chlorine on the right, 1 silver on the left, 1 silver on the right. I've got 1 acetate on the left, 1 on the right. This guy is already balanced. Nothing extra that I have to do. Whoops. There we go. All right, you know what? We'll do the acid and base in a bit. Let's go ahead and try this one, if you would. See if you can do this on your own. See if you can figure out what you've got to do. And so we take a look at this. The first thing I see is that I've got 2 nitrates. I need to fix that. So I'm going to put a 2 in front. I've got 1 nickel on the left. I've got 1 nickel on the right. I've got 2 hydrogens on the right. I've got 2 hydrogens on the left. We are now balanced. All right, we've got barium hydrogen carbonate or barium bicarbonate, and this is going to decompose into barium carbonate, barium carbonate, water, and carbon dioxide. All right, let's take a look at this. So I've got, this is a little trickier. So I've got CO3, I've got 2 of them. There's 1 carbonate, there's CO2, and then another oxygen. I've got 2 hydrogen there. I've got 2 hydrogen there. Remember, this parentheses means that we have 2 HCO3s present. This guy is already balanced, which is nice because that could have been a little tricky. All right, we've got barium chloride and sodium sulfate is going to form sodium chloride and barium sulfate. I see right off the bat I don't have enough chlorines, so I put a 2 in front of there. I need 2 sodiums, which I now have with the sodium chloride. I've got 1 barium and 1 sulfate. This guy is done. All right, we've got aluminum carbonate is going to form aluminum oxide and carbon dioxide. All right, I got a problem in that I need some carbonates, or I need some carbon. So how about if we put a 3 in front of this guy? Now in doing so, I now have 6 oxygens here plus these 3. So that gives me a total of 9 oxygens, which is delightful because I need 9 oxygens for my aluminum carbonate. And this guy is balanced. All right. Now, if you want to take a look at this guy right here, sometimes it's easier to look at water as HOH. It's just a hydrogen attached to a hydroxide. All right, so I've got 3 magnesiums. So let's go ahead and put a 3 in front of this guy. I've got 3 magnesiums. I need 2 phosphates. So I'm going to put a 2 in front of that guy. How many hydroxides am I going to need? Well, remember you have to multiply the coefficient by the subscript. So I need 6 hydroxides and I need 6 hydrogens. Well, if I put a 6 in front of this, I'm going to have 6 hydrogens and I'm going to have 6 hydroxides. And now I'm balanced. To be honest with you, these get pretty easy, but the bottom line is you got to practice them. And so you'll have a whole series of activities to do to practice balancing equations. All right, next time we'll get into the different categories of types of reactions. See you next time.